Hello friends, this is lecture 13 of group theory and today we are going to study about factor groups. Factor groups are also known as quotient groups. So as we have already seen about normal subgroups in the previous two lectures, factor groups are related to normal subgroups. Let us see how you are going to make a factor group, how a factor group is formed. Let me just tell you some basic about the factor groups. So you have a group and you have a subgroup of that group. And that subgroup is normal subgroup. And about normal subgroup, you already know. Subgroup is normal if and only if where every right coset is equal to say some left coset. And there were some other equivalent conditions also for a subgroup to be normal. There was a normal subgroup test also. So we have seen that if H is a subgroup of G, then H is normal subgroup if and only if HG is equal to GH, means the right coset is equal to the left coset, then we say that the subgroup is normal. Now, why we are saying that normal subgroups are of this much importance? Normal subgroups are very important in group theory because they are used to form the factor groups. So when you're talking about factor group means you have a group G and you have a subgroup, a normal subgroup H of G, then factor group is the collection of all the right cosets of H in G, or you can say it is the collection of all the left cosets of H in G. So till now you have seen that if you have a group and you have a subgroup, then how to make how to write all the cosets of that subgroup in the group. Now we are saying that the collection of all the cosets, the collection of all the distinct left cosets, or we can say the collection of all the right cosets of H in G, that forms a group, and that group is called a factor group. So basically you have a group G and a normal subgroup H, then G upon H is the factor group or the quotient group, because you are writing it as G upon H. So you can just visualize that it is the factor group in that sense. Now let us continue this. Let me read it for you. When H is a normal subgroup of G, then the collection of all the left cosets of H in G itself forms a group. As I told you, you collect all the left cosets of the subgroup in the group, then that collection forms a group. And if you are saying that a collection is forming a group, then that means every subgroup, every group is, every collection forms a group under some binary composition. Then what is the binary composition here? The set is of all the cosets. So how you are going to combine those cosets? So if the binary composition means you are combining two cosets and you again get a coset of that subgroup in the group. So now we are going to see what is that binary composition by which you are going to combine two cosets and you are still in the same set. That is, you are getting the coset, whether left coset or right coset, whatever you are talking about. So this is the notation of a factor group. So H is the normal subgroup of G, then G upon H, this is normal, this is a factor group. And as I told you, factor group is the collection of all the left cosets or right coset. You can write here, I have used the left coset notation. So G upon H is equal to AH such that A belongs to G. So this is your factor group. Now we are saying that this collection AH such that A belongs to G, that is the collection of all the left cosets of H in G, this forms a group. Now we will prove that this collection is a group. And the binary operation is this. We are going to show that G upon H forms a group under this operation. You take two cosets AH and BH, where A and B are elements of G. Then AH is combined with BH and you are getting another coset ABH. So this is the operation by which you are combining two elements of that collection. So we are going to prove that with respect to this operation, the collection of all the left cosets of H in G forms a group, and that group is called the quotient group or the factor group. So first of all, you just observe that the binary operation which we have taken, this which was combining the two left cosets. So this binary operation, this is from the collection of that is from G upon H to G upon H. That is, you are combining two elements of G upon H. That means this is from G upon H cross G upon H to G upon H. So we are going to prove that this binary operation is basically a function, and it is a well-defined function. So this correspondence defined in one is actually a well-defined function. So for proving that, suppose that AH is equal to A dash H and BH is equal to B dash H. So if AH is equal to A dash H, that means your A dash is equal to A into H1 for some H1 belongs to the subgroup H, and B dash will be is equal to BH2 for some H2 belongs to H. Therefore, A dash B dash H will be, now you just substitute the values of A dash and B dash. So this will be AH1 into BH2 H. Now, this is the next step. Here what we are doing, we are writing it as A H1 BH, because this is your H2H and H2 belongs to H. So H2H will be equal to H. This property we have already seen in the properties of cosets. So this will be your H. Now BH will be equal to HB, because H is a normal subgroup. So every left coset is a right coset. So BH can be written as HB. Now H1H can be written as H, because H1 belongs to capital H. So this will be equal to H. So this is equal to your AHB. Now HB can be written as BH, as H is a normal subgroup. So this will be equal to ABH. So A dash B dash H is equal to ABH. Thus the operation defined in one is a well-defined operation. So now that we have proved that the operation is well-defined operation, now we will prove all the other properties of a group, like closure property, then associativity, existence of identity, and existence of inverse for every element. So let us see all the properties one by one. So for proving those properties, let us take these three elements in G upon H, X, Y, Z. So X, Y, Z are in G upon H. So these are all cosets. So let us write them as cosets. So X will be equal to AH for some A in the group, Y will be equal to BH for some B in the group, and Z will be equal to CH for some C belong to the group. So suppose these are the three elements of G upon H. Then first see the closure property. So X into Y will be AH into BH, and this will be equal to ABH. So this, and ABH belongs to G upon H, because if A and B are elements of G, then A into B is also element of G by the closure property, as G is a group. So closure property holds here. Now associativity, X, Y into Z. This is equal to AH, BH into CH. Now AH into BH will be equal to ABH, and this is CH. Now this product will be equal to AB into CH. Now by associativity, you can write it as A into BCH. So you can just break it as AH into BCH. Now BCH can be written as BH into CH. So what is this? This is your X and this is your Y, this is your Z. So you have shown that XYZ is equal to X into YZ. So associativity holds in G upon H. Now existence of identity element in G upon H. So identity means such an element in G upon H such that when you multiply that element with any other element of G upon H, then there is no change in that element. So here H, in G upon H, this H is the identity of G upon H. So let us see. You just multiply h with any other element. So x is an element of g upon h. I'm going to multiply x by h. So what is your xh? Xh, this x is equal to ah, and h can be written as eh. So this is equal to AEH, and your AE will be equal to A. So this is your AH and AH is your X. So XH is equal to X. Similarly, you can show that HX is also equal to X for every X in G upon H. So H is the identity element basically. So G upon H is the collection of all the left cosets of H in G, and you know that H itself is a coset. When you write all the coset, then H always comes there. So H is the, so in G upon H, H is the identity element. Now, number 4, that is the existence of inverse for every element of G upon H. So consider X, which is AH. This belongs to G upon H, be any element. Now, X dash, which is A inverse H. Now, you know that if A is an element of the group, then A inverse also belongs to the group. So G is a group, though. So every element of G has its inverse in G. So A inverse belongs to G. That means x dash, you can take x dash equal to A inverse H. So you can take this element A inverse H. Now we are saying that this A inverse H, this x dash is basically the inverse of x. So for that, let us check that what is x into x dash. So x into x dash should become identity. So x dash is AH into A inverse H. So this will be equal to A inverse H. Now what is A inverse? A inverse is identity. So this is equal to H. That means x dash is the inverse of x. Similarly, you can prove that x dash into x is also the identity. Identity means H. H is the, because H was the identity element. So here we have seen that this collection G upon H is satisfying all the properties of a group with respect to the operation which is defined in this number 1 here. So I hope you have understood the proof of this theorem. So now let us see a few examples. So here, this example, you have this set 4z. Z is the set of integers. So 4z will be multiples of 4. So 0 plus minus 4 plus minus 8 and so on. This is your 4z. So you have to construct z upon 4z. So in the subgroup, when we were discussing about the subgroups, we have seen that this 4z is a subgroup of z. In fact, it is a normal subgroup of z that you can verify. Here now we have to write all the elements of z upon 4z. So what is your z upon 4z? Z upon 4z is the collection of all the left cosets of 4z in z, or all the right cosets of 4z in z. So let us first determine the left cosets of 4z in z. So left coset means you are adding from the left, because z is the group under addition. So here you will be taking addition. So you just take one by one all the elements of z. First we are taking 0 plus 4z. So 0 plus 4z will be 4z. So this is 4z. Now next is 1 plus 4z. 1 plus 4z means you are just adding 1 to all the elements of this 4z. So this will be 1. First you consider all the positives. So 1, 5, 9 and so on. And when you are taking the negatives, so when you are taking 1 here, so 1 minus 4 will be minus 3, 1 minus 8 will be minus 7 and so on. So you will get a set like this: 1 plus 4z, 2 plus 4z will be this, 2, 6, 10 and so on. This will be minus 2, minus 6, minus 10 and so on. 3 plus 4z is this. Now what is 4 plus 4z? Basically 4 plus 4z will give you the element from here only. Then 5 plus 4z will be this, 6 plus 4z will be this. So you will get a repetition here. So all the other cosets will be from this collection only. Now We will prove that whenever you take any other coset, that will be from this set only. We claim that there are no other cosets of 4z in Z except these 4 cosets. So we are claiming that there are no other cosets of 4z in Z. So so मान लीजिए कि कोई और दूसरा कोसेट है फॉर इफ k belongs to z. So k हमने कोई एक दूसरा एलिमेंट ले लिया z का, कोई इंटीजर ले लिया, k belongs to z, then k can be written like this: k is equal to 4q plus r. So if you are writing k is equal to 4q plus r, this is by division algorithm. You can write k is equal to 4q plus r, where your r is less than 4 obviously. So this r is greater than equal to 0 and less than 4. So you are writing now k plus 4z. K you have taken any other integer from z, and you are trying to find out the structure of k plus 4z, how k plus 4z looks. So we are trying to prove that k plus 4z is from these 4 cosets. So k plus 4z, so what is value of k that you have taken? K will be 4q plus r, and this is your 4z. So 4q plus 4z will be 4z only. So this is this thing will be absorbed in 4z. So this will be equal to r plus 4z. And what is r? Your r is greater than equal to 0 and less than 4. That means the r is 0, 1, 2, 3. So this is basically from this set only. So your r plus 4z, that means k plus 4z will be from those 4 cosets only. So this collection will be 0 plus 4z, 1 plus 4z, 2 plus 4z, 3 plus 4z. So this 0 plus 4z is basically the 4z, the identity. Now we have formed the scale is table for this vector group z upon 4z. So you just write all the elements here, and then row wise also now we have combined these elements. So 0 plus 4z, you are adding them. So 0 plus 4z plus 0 plus 4z will be 0 plus 4z. You are adding this 0 plus 4z with 1 plus 4z. So because this is the identity element, you are adding this with all the other elements, so there will be no change. Now 1 plus 4z, so 1 plus 4z plus 0 plus 4z will be 1 plus 0 plus 4z. So 1 plus 0 is 1, so this is 1 plus 4z. Now this and this, so 1 plus 1 is 2, so this is 2 plus 4z. Now this element and this element, so this is 1, this is 2, 1 plus 2 is 3, so this is 3 plus 4z. And here 1 and 3 is 4, so 4 plus 4z, 4 plus 4z is basically 0 plus 4z. This is your 0 plus 4z. You can say that you are taking under modulo 4. So here now 2 plus 4z plus 0 plus 4z is 2 plus 4z. This is 2 plus 1 is 3, then 2 plus 2 is 4, that will be 0 plus 4z. Now 2 plus 3 is 5, so that will be 1 plus 4z under modulo 4. Now 3 plus 0 is 3, 3 plus 1 is 4, the 4 that will be equal to 0. Now this 3 plus 2 is 5, that will be equal to 1, 3 plus 3 is 6, that will be equal to 2. So from this table you can just realize that this Kelly's table is same as the table when you were considering a group in the previous chapters. And what was that group? That was your Z4. What is your Z4? Z4 is 0, 1, 2, 3 under modulo 4. So if you combine, if you take 0, 1, 2, 3, these elements only. Now forget about 4z. You are taking 0, 1, 2, 3 here and 0, 1, 2, 3 here. You just add them under modulo 4. So you will be getting all these elements 0, 1, 2, 3, 1, 2, 3, 0, 2, 3, 0, 1 and 3, 0, 1, 2. So now this here you are getting 4z, 4z also. So here we are saying that z upon 4z is isomorphic to z4. So both have same structures. So there is a generalization also. You take any nz, then z upon nz, this quotient group is isomorphic to zn. Now this is another example. Here we have taken group as Z18 and H is a subgroup which is generated by 6. So this will have 3 elements 0, 6 and 12. So 12 plus 6 will be 18. So that will be your identity, that will give you 0. So these three elements will be there in a subgroup which is generated by 6. Now this is a normal subgroup that you can verify. Now we want to find G upon H, the factor group, the quotient group of H in G. So we are saying that G upon H is a collection of these elements: 0 plus H, 1 plus H, 2 plus H, 3 plus H, 4 plus H, and 5 plus H. Since H is a subgroup which is generated by 6, therefore it will absorb all the multiples of 6. When you will take the 6 plus H, so that will be equal to 0 plus H, then 7 plus H will be equal to 1 plus H, and so on. So now here we have shown that how you are going to combine two elements of G upon H. If you are taking 5 plus H and 4 plus H. So 5 plus H plus 4 plus H will be 5 plus 4 is 9. So this will be 9 plus H, and 9 plus H can be written as 9 can be written as 3 plus 6, and 6 plus H is equal to 6. 6 plus H is equal to H because 6 belongs to H. Your H is a subgroup which is generated by 6. So 6 belongs to H. So if you are writing 6 plus H, then 6 plus H is equal to H. This element is in H. So this element will be absorbed by H. So this will be basically equal to H. So 5 plus H plus 4 plus H is giving you 3 plus H. So this is how you can combine these elements of this group G upon H, and whenever you are taking more elements 6 plus H, 7 plus H, then you can understand how those elements are from this set only. Now there is another example. This is basically an exercise for you. Here we are saying that S3 is a group and N is this subgroup, which is a normal subgroup. Now this is an exercise that you have to find all the this factor group of N and G, S3 upon N, all the elements you have to find. So in this today's lecture, we have learned about the factor groups or the quotient groups, and for that the background that you need is the normal subgroups. And for normal subgroup you should know what is a subgroup, and for a subgroup you should know what is a group. So this is a chain. First you have studied about groups, then we have seen subgroups. When you know all the conditions, and many examples of subgroups that you have seen, after that we went through normal subgroups, and we said that normal subgroups are of central importance in group theory. Why they were of this much importance? Because we have to see this factor groups also. Factor group you cannot make a factor group without a normal subgroup. So this is all about factor groups. You can see more examples and exercises from the group. All this material is taken from a contemporary abstract algebra book, 4th edition by Joseph A. Gillian. You can see the latest edition also. There you may find more examples on factor groups. So in the next lecture, we are going to start a new topic in algebra. So this group theory, I'm going to end group theory here. You can try more exercises. So in the next lecture, we are going to see a new topic. So till then, bye-bye. Take care.